In this video, we'll talk about object-relational mapping using the Java Persistence API and the very popular Java ORM library called Hibernate. Let's start with the object-oriented paradigm we learned in our programming classes. It basically says that our world consists of objects. So object-oriented programming languages like Java are good because they can be used to model the real world more closely and more easily. After using OO language for a while, most of us probably would agree that this is indeed the case. To continue with this line of thought, we'd think that for data storage, we'd want to use object-oriented databases too. So if there are some objects in our program that we want to save, we can save them directly in a database, just like saving them in memory. The problem is that despite lots of efforts spent on the research and development of object-oriented databases, relational databases are still the most reliable and the most widely used and supported database systems these days. What this means is that there's often this mismatch between our applications, which are usually written in object-oriented languages, and our data storage, which is usually relational. There are two ways to bridge this gap: core-level interface and embedded SQL, which we studied in other classes, and the object-relational mapping, which we'll discuss in this video. Most of you are familiar with core-level interface, where an application interacts with a database through function or method calls. The way it works is that the application creates a SQL statement in the form of a string, and this string is passed to a method as a parameter. The method then sends a string to the database, which runs it as a SQL statement. The results of the statements are sent back from the database, and the method returns the results as the return value. The example shown here is in Java, but it's pretty much the same in other languages. Another way to access a database is to embed SQL directly in the program. The example shown here is embedded SQL for Java. An important advantage of embedded SQL is that SQL statements are recognized as special statements instead of just as strings. So it's possible to detect SQL syntax errors during compilation rather than waiting for runtime errors. The downside, however, is that we cannot use a regular Java compiler to compile this code because it's not Java anymore. We'll need to first use a pre-compiler to convert this code into regular Java code and then compile it. This additional requirement of tool support is probably why embedded SQL is not nearly as popular as CLI. Regardless, note that in both CLI and embedded SQL, it's the application developer's responsibility to convert between application objects and the database rows and columns. And this could lead to some problems as shown in our next example. Here I have a Java class that represents employees. An employee has an ID, a name, and a supervisor, who is an employee him or herself. This is a pretty standard object-oriented design. And here's the database table design if we want to store the employee information in a relational database. The table has 3 columns: ID, name, and supervisor ID. Comparing this with the Java class, we can see that here, supervisor is of employee type in the Java class. And here, it is an integer field storing the supervisor's ID because there's no class type in relational model. We can use a supervisor ID to find the record of the supervisor. Just like in the object-oriented design, the supervisor field is actually a reference to the actual supervisor object. In other words, this is the relational equivalent of the OO design. It's a pretty standard design and there's nothing wrong with this. So far so good, right? With a pretty simple problem and good designs on both sides, you'll think that there won't be any problem. Well, that's not quite the case. Considering this example, suppose we want to write a constructor for this class. This constructor takes an employee ID as a parameter, uses the ID to query the database, and then construct an employee object based on the results. The code would look something like this. The first thing we notice is that SQL is hard-coded in the application. Because each database system has its own SQL dialect, if we want to switch to a different database system, this could become a problem because we'll have to check and potentially change lots of Java code. With that said, switching database system really doesn't happen all that often. So although hard coding SQL could potentially be a problem, it's not too big a deal. Now here's a bigger problem. After the query completes and the results sent back from the database, we have to manually convert rows and columns into objects. It doesn't look too bad in this example, and that's because our class only has 3 fields. In a more realistic example, like the user class in CSNS2, here, you can see that there are more than 30 fields in this class. And if we have to do result set get string, result set get int, and so on for each one of those fields, it's very tedious. But then again, we are software developers and we are paid to write code. Even though sometimes it's tedious code, it's probably still not a deal breaker. But how about this problem? Here, notice that the supervisor field of the employee class is of employee type, but the supervisor ID in the employees table is integer. It will be an error if we simply try to do supervisor is result set get int supervisor ID, because we cannot assign an integer to an employee reference. So how do we do this? One solution may be doing a recursive call like this. This actually kind of looks neat and works as long as the recursion stops when we get to an employee who doesn't have a supervisor, presumably the head of the company. The problem of this is that although we just want one employee object, this will create a lot more objects, including the employee supervisor, the supervisor's supervisor, and so on and so forth, all the way up to the head of the company. And obviously, this is quite inefficient. So how do we deal with this? If you think about what you did when you use, for example, JDBC for database access, you'll realize that this is probably what you did when you were in a similar situation. Instead of designing your class using an object-oriented approach, you'll probably just set integer supervisor ID like this. Now, here lies the biggest problem caused by the paradigm mismatch between the application and the data storage. When you use a relational database for storage, it forces you to design your data model classes just to be like tables. Or in other words, although this is a class, it's based on a relational design rather than an object-oriented design. So we are losing the benefits of using an object-oriented language simply because we have to use a relational database for storage. So how do we solve the problem of the paradigm mismatch between our object-oriented application and the relational storage? Well, this is where object-relational mapping comes in. As the name suggests, it's a layer that sits between the application and the relational data storage, and it's responsible for translating between objects in the application and rows and columns in the database. ORM is very popular these days, and many languages have their own ORM solutions. In Java, the mainstream ORM solution is Java Persistence API and Hibernate. JPA defines three things: a set of annotations used for mapping Java classes to relational tables, a data access API, kind of like JDBC, and an object-oriented query language, JPQL. It's like SQL, except that SQL works on tables and rows and columns, while JPQL works on classes and objects and properties. As the name suggests, JPA is an API, which means it's an interface, not an implementation. Just like when you use JDBC, you need a JDBC driver which implements the JDBC API. When you use JPA, you need a JPA implementation. And that's where Hibernate comes in. Hibernate is the most popular Java ORM library, and in fact, it almost single-handedly popularized ORM in Java development. The development of Hibernate actually preceded the JPA standard. Therefore, there are two ways to use Hibernate. You can use the native Hibernate API without using JPA. And this allows you to access some Hibernate features that are not available in JPA. The other way is to use Hibernate as a JPA implementation. The benefit of doing this is better portability in the sense that if you are not happy with Hibernate, you can replace it with another JPA implementation without changing your code. Another benefit is that the behaviors of the operations tend to be better defined and documented in JPA. So in this class, we'll take the second approach. Let's see how it works with an example. This example only has a few files: a model class, some code that shows how to load an object, save an object, search an object, and so on, and a configuration file that includes the database information and a configuration file for the logging tool used by Hibernate. We'll ignore the logging configuration for now, as it's not a required file, and also because we'll discuss logging in more details in another lesson. Let's first look at the data model class. As we can see, it's a pretty simple class with three fields: ID, name, supervisor, and some getters and setters: get ID, set ID, get name, set name, get supervisor, set supervisor. Nothing too special. This, by the way, is the same class in our previous example, the employee class, before we change it to supervisor ID. Notice that here, supervisor is indeed an employee, not just an integer. The employee class is a very typical so-called persistent class, which basically means we want to save the objects of this class in a database. And those objects are called, of course, persistent objects. As we just saw, a persistent class really is just a model class in an MVC application. With that said, it is recommended that a persistent class meets some additional requirements. First, it should have an ID field, like this. This field is the primary key field of the table this class is going to be mapped to. Second, this class should implement the serializable interface. There's no method in the serializable interface, so you don't need to write any additional code to implement it. Implementing this interface simply tells the Java virtual machine that the objects of this class can be converted to binary form and back. The main purpose of this requirement is to allow the object caching function in the ORM to save the cached objects on disk when the memory cache is full. The last recommendation is that all persistent fields, meaning the fields you want to save to database, must have getters and setters. Note that those getters and setters don't have to be public, so this requirement won't break the encapsulation design of the class. All in all, as we can see, it doesn't take much to make a typical model class a persistent class, as we usually do this in a model class anyway, and not to mention that these requirements are recommended but not required. The takeaway here is that you can design your model classes as you see fit, and they can be used as persistent classes with little or no change. But of course, there's no magic in software development. We do need to specify how this model class is mapped to a table. And this is where we use these annotations. We'll talk more about the mapping annotations in the next video, but here are a few that are most commonly used. A persistent class needs to be annotated with entity. By default, when you annotate it with entity, it's mapped to a table with the same name as the class name. But usually I use different naming conventions for Java code and SQL. So here I'm using another annotation table. And this annotation, I use it to specify that the table name should be employees with a lowercase e and the plural form instead of the employee class name. ID, of course, is for the ID field. More often than not, you'll also want to use generated value with ID. This one tells the database to use its default method to generate new unique IDs. Fields of simple types like numbers and strings can be annotated with basic, which can be omitted. Class types needs to be annotated with many-to-one, one-to-many, many-to-many, one-to-one, depending on the relationship type between the class and the other class. For example, here, each employee only has one supervisor, and one supervisor can supervise many employees. So between employee and supervisor is a one-to-many, many-to-one relationship. The annotation here is many-to-one because many employees have one supervisor. All in all, as we can see, annotations are mostly pretty straightforward. And with these annotations, the ORM tool knows how this class is mapped to a database table. And speaking of database table, I already created the tables in my database. If we do a select on the employees, let me log in. If I do a select on the employees table, you can see that I have 3 records here, Sue, Joe, and Tom. Joe's supervisor is Sue, Tom's supervisor is Joe, and Sue doesn't have a supervisor. Presumably, she's the head of the company. Of course, we also need to specify the information about the database so our application can connect to it. And this information is in this file. This file is a special file called persistence.xml, and in Eclipse, by default, it shows you this view, but click the source tab and it will show you the source code of the file. This file is required by JPA, and it has to be called persistence.xml, and it has to be under a folder called meta-inf under the class path. So in a Maven project, the right place to put it is under source main / resources / meta-inf. As we can see here, in this file, we need to specify something called persistence unit. And we have to specify a provider for this persistence unit. Because we are using Hibernate as our JPA implementation, the provider is a Hibernate class. If you use a different JPA implementation, just replace this with a class from that implementation. As for the properties, notice that some of them are standard JPA properties with names like javax.persistence.something. And the database URL, username, password are specified with those properties. And then there are some properties specific to the provider that control how the provider works. The Hibernate.dialect property here tells Hibernate that the underlying database is a MySQL version 8 database. So Hibernate will generate SQL statements in MySQL version 8 dialect. And here we set show SQL to false, and later on we can change it to true to see the SQL statements generated by Hibernate. One last thing before we see how the whole thing works. Remember that in JDBC we use connection statement, prepare statement, result set, and so on to access a database. With JPA, we have a similar set of classes, interfaces, and methods for database access, except of course the data is now accessed as objects instead of rows and columns. The most important interface is Entity Manager. After class, please take a look at the Entity Manager documentation here. So you can have a general idea of what methods it provides. Basically, all the database access will be done through these methods. Here, I listed the most commonly used Entity Manager methods. We are going to see these methods in action in the example. Okay, so back to the example, we have seen the model class or the persistence class with annotations, and we have seen persistence.xml file with all the database information and the ORM configuration properties. And now let's see how this thing works. So first, in order to interact with a database, we need to create an Entity Manager factory. The code will look for persistence.xml file and then find the persistence unit with the given name. So notice that the persistence unit name here is called Hibernate-examples. And here, when you create the Entity Manager, you have to use the same persistence unit name so that it knows which set of parameters it needs to use in order to connect to the database. After that, we can then create an Entity Manager object, which is kind of like a connection object in JDBC, and we can use it to access the database. So first, let's say we want to find the employee whose ID is 3. We'll use the find method here. It takes an entity class and then a primary key value to find the object. So we'll say employee, we'll call it E3, and we'll say entity manager find, and we need to give it a class, and we'll tell it this object is in this employee class, and the primary key value of the object is 3. And if we look at our database, we should get Tom here. So let's print out e3.getName, and we can run this. So it's just a Java program, so just run it as Java application. And it shows indeed Tom here. So this is the first example, and it's pretty simple, but note that it returns an employee object directly. There's no need to do the result set get int or result set get string stuff. We get an object back. We don't have to manually convert columns into object properties and so on and so forth. And then let's say we want the employee number 3's supervisor. Now in SQL, you actually need to do something fairly complex. For example, if you want to do something like this in SQL using the table, you would have to do something like select something from employees E1, employees E2, employees E3, where E1's supervisor ID is E2's ID and E2's supervisor ID is E3's ID and E1's ID is 3, something like this. And then you select E3 star. Now, this is a table that has to self-join with itself twice. But using an ORM tool, since we already have the E3 object here, all we need to do is print out the supervisor's name. We can simply say E3 get supervisor again, and then get name. And that's it. So if we run this code, we can see that it gets Sue, which indeed is Tom's supervisor's supervisor. So this is the beauty of good object-oriented design and ORM working together. Because supervisor is an employee rather than just a supervisor ID, we can simply do get supervisor without writing any additional SQL statements. Of course, although we don't need to write any additional SQL statements, it doesn't mean we don't need SQL to get the data. If we change this one to true, so that Hibernate will print out the SQL statement it generates, and if we run this again, we can see that behind the scene, actually Hibernate is generating all the SQL statements for us. So that's pretty convenient. what happens to this? Why all of a sudden it has colors? Well, let's ignore them. Okay, so now what about creating a new employee? Well, since we are using ORM, it's basically creating a new object, then save the object to the database. So let me write out the code and then we'll explain a little bit. So let's say we want to create a new employee. So we'll say this employee is a new employee. And this new employee's name will be Jack. And this new employee's supervisor, let's say Tom is his supervisor. And then we need to save this employee to the database. And that takes a little bit more code than before. So we'll have to say entity manager get transaction begin, and then we'll need to say entity manager merge, and then we'll have to say entity manager get transaction commit, and that should do the trick. So let me run this to make sure that it actually works, and then we'll explain. So if we go back to our database and we look at the table, we can see that now Jack is inserted into the table. So the code does work, and all in all, it's still much cleaner than doing an insert statement, but it does involve a little bit more than before. So first, about this transaction begin, transaction commit thing. JPA requires a transaction to be used whenever we try to write to a database. So if we just search a database, it's considered reading the database, and there's no change to the database. But insert, update, and delete are all considered writing to a database because they change the data in the database. And JPA require a transaction to be used whenever we try to write to a database. Transaction is actually a very important thing in relational databases. We'll talk about them more later when we compare relational and NoSQL databases. For now, just remember that you need to start a transaction and then commit it after writing to a database. Okay, so the second thing we need to explain a little bit is this merge method. Merge saves our object to a database, as we just saw, and it also returns a reference to a so-called managed object, and that's something we need to explain. What is a managed object? So let's look at this example. In this example, we have an object F1, which is loaded from the database using an entity manager. And in this case, F1 is called a managed object because, of course, it's managed by the entity manager. Now, if we create a new object using the new operator, then this object F2 is called an unmanaged object because the entity manager is not aware of this object. And if later on we close the entity manager, closing an entity manager will not automatically remove all the managed objects from memory. Those objects are still there in the memory, but now they become detached, meaning that although they still exist there, they are no longer related to a database connection or entity manager, or sometimes called persistence context. Note that all the ORM magic only works on managed objects. For example, if we try to do an employee get supervisor on an unmanaged object or a detached object, you'll get an exception or a null. Merge is a pretty flexible method. It can be used on all three types of objects. But depending on whether the original object is managed or not, the return value of merge is different. In particular, if the original object is a managed object, the return value is the same as the object. But if the original object is unmanaged or detached, the return value is a managed copy of the original object. In practice, you almost always want to use the object returned by merge, not the one passed to merge. So if you look at the code here, you can see that we are creating a new object which is unmanaged. And then we pass that unmanaged object to merge, and this will create a new managed copy of the object and returned by merge. And we are assigning that returned managed copy to new employee. So after this call, this employee is no longer the original object. This is kind of important, even though it's a kind of very easy to miss detail. Later on, if you write code, if you miss this part, for example, you'll see that if you try to use new employee, it's as if that new employee is never saved, and that's because it's still the original unmanaged copy. And after merging it, you want to use a merged copy returned by merge, managed copy returned by merge. Okay, so one more example. What if we need to write some query? Like in this case, we want to find all the employees who are supervised by employee number 1. And this indeed takes a query. And again, let's first write the code and then we'll explain it. First, I'm going to write the query. It looks actually quite similar to SQL. So I'm going to say from employee where supervisor is supervisor. So if you remember JDBC and prepared statement, you know that in prepared statement, oftentimes you have these placeholders where you can later on set values to these placeholders. It's the same thing here, except that now we can name these placeholders. In JDBC prepared statement, you have to use the index of the placeholders, but here we can give them names. So this column supervisor is basically a placeholder with the name supervisor, and later on we can set a value to it. And after that, we can create a query. So we'll say entity manager create query. So there are many, not create name query, create query. There are several forms of create query. The one we want to use is similar to the one that's used in find. It will take a class which is a class of the return objects, and then it will take the query itself. So it will be something like employee class, and it will take this query. So now I think I may have got the order wrong, so it's query first and class second. Yeah, okay. So query first, class second, unlike in the find. Okay, so once we have a query, we can chain another method to it, and this time we set the parameter. So as in JDBC, we could use position, or we could use the placeholder name. So here I'm going to use placeholder name and say set the value of supervisor to be E3, because we are trying to look for people who are supervised by employee number 3. Okay? And then we can chain yet another method to it by saying get result list, which is this one. And this will return all the employees who are supervised by E3 as a list of employee objects. So we'll get the results here. We'll call it employees. And then we can iterate through it and print out the names. We'll say employee, employees, and we'll print out e's name. Okay, so let's run this again. Notice that it prints out Jack twice, and that's because we inserted another employee Jack here, and if we go back to our table, we can see that now we have 2 Jacks, and that's fine. So now let's go back to this query and see what's going on. The most important thing about this query is that it's a query about classes and objects and properties, not about tables and rows and columns. Notice that our table name is called employees, but here we are not selecting from employees. We are selecting employee, which is the class name. What this query says is that select all the objects in class employee where the property supervisor is a given value. Again, notice that the column here is actually supervisor ID, but we are not specifying the column. We are specifying the property supervisor, which is property here. And also because this is selecting objects, not columns, the select clause can be omitted, unlike in SQL. In SQL, you would say select something from tables and so on, right? But here we are selecting objects, not individual columns. So we can omit the select clause because we are just getting all the properties of all the objects. And consequently, the results is a list of employee objects. And again, we don't have to construct objects from rows ourselves. And this is the query and look at the supervisor. Notice that because we are specifying the supervisor property, we are actually passing an object as the value of the parameter. We're not passing a supervisor ID or anything. We are passing an object here. And also because this is a property, it allows us to do fancier stuff, like if you want a supervisor, you can say supervisor or .id or something like that. And it basically follows Java property rules. If you remember, when you do JSP programming using expression language, you can chain properties together by using property dot property dot property and so on. It's the same idea here. If a property is an object that has its own properties, you can use dot to specify that property. The query language used here is called Java Persistence Query Language, or JPQL. It's a query language used in JPA. The syntax is similar to SQL, but it operates on classes, objects, and properties instead of tables, rows, and columns. The ORM tool automatically translates it into different dialects of different database systems. So if you switch to a different database system, you don't need to change your database code. The query we used in the code is actually not exactly JPQL. It's Hibernate's version of JPQL called HQL, or Hibernate Query Language. HQL supports all the JPQL syntax plus some more. Because HQL is very similar to SQL, which everybody is supposed to be familiar with already, I'm not going to discuss HQL in details. We'll see a few more examples down the line, but for the most part, you'll need to figure out how to do it yourself. You can check out some examples in CSNS2 code. You can get CSNS2 source code from GitHub. Here, and if you look at the source code, under model, there are many packages that ends in JPA. Those are DAO implementation classes using JPA. And for example, if you open up file DAO implementation.java, you'll see a bunch of queries that queries the file class. So there are many examples in CSNS2, and in this class, the HQL queries that you are going to write generally are of the same level or easier than the ones that you can find here. So again, it's very similar to SQL. Take a look at a few examples, you'll get the general idea of it. And for specific things or for specific details, of course, you can always check out the documentation. So to summarize, the most important benefit of ORM, in my opinion, is that it allows applications to be designed in true object-oriented manner instead of designing classes that look like tables. And there are also some more practical benefits. In particular, data access with ORM is much simpler and easier because data is accessed as objects. So no manual conversion between objects and rows and columns is necessary. Also, JPQL/HQL queries are usually simpler than SQL queries. And in many cases, we don't even need to write any query because the ORM tool will automatically generate the query for us. Because of the use of JPA and JPQL/HQL, we can switch to a different DBMS fairly easily. And on top of all that, ORM tools usually do object caching, which is quite beneficial to application application performance. So this is a quick introduction to ORM. We'll talk more about JPA and Hibernate in the next video.